Thank you. First, thank you very much for the invitation to talk at this wonderful conference. I think it's very much the credit of all the people who presented the talks that despite the incredible breadth of subjects, at least I think I got a lot out of talks, even from very far from my own area of expertise. Thanks very much. It's great. I'm at IISc, and I'm also have a connection to ICTS officially these days. And I'll tell you this is a talk based actually on one piece of work, resulting in one paper rather than some kind of a rambling overview. So let's get started. So the reason I decided to talk on this is that it's got both a French and an ICTS connection. It's really work owned and driven by the extraordinary Thibaut Arnoux de Piret, who was a postdoc with Yariv Kafri at Technion, and then a C.V. Raman postdoc at IISc, and now is at IPHT. And it started just outside this room. Yariv and I were sort of standing and chatting about something, and really Yariv posed a question which resulted in this work, and you can read about it in this article which came out a few weeks ago. So I'll introduce the topic, and I'll tell you about some earlier work which sets the background for this, and then tell you about the problem that we actually solved, namely an inclusion in a fluid full of swimmers, and then I'll summarize. I think unlike my usual talks, I have a feeling that actually there are fewer slides than there should be. So there'll be lots of time for questions. Okay, so the problem we're interested in really is, you could kind of imagine, I mean, this is a false analogy, but imagine an ocean in which there's a bunch of fish swimming around and there's an island somewhere. I'll tell you why it's a false analogy. And then you're sort of asking about how the distribution of the fish reflects the presence and structure of the inclusion. It's not quite that for a variety of reasons. Major reason being is we're talking about very slow, small swimmers, not fish. And the inclusion isn't anchored in the ground. We're thinking about a bulk fluid. But in any case, it's micro swimmers in a fluid containing an object. And the case of greatest interest is when the object has a structural polarity. So it's got some kind of head-tail distinction. This turns out to be an important specific property. Okay? You could imagine many different shapes of inclusion. What's important for today's talk is really an inclusion which has a well-defined polarity. It might or might not have additional symmetries or asymmetries. So you can imagine a polar and axisymmetric inclusion. You can imagine an inclusion with a well-defined polarity, but also, it sort of has a front and a back, and maybe it has one arm sticking out, or these kind. These broadly are the two cases I'll talk about. And I mean, if you like, what's really being said is you've got this inclusion, you've got the far field. There's of course going to be fluid flow in the far field because of swimmers and this object. And there's also going to be how the swimmers themselves are distributed. And the question is the degree to which what's going on at that obstacle in the fluid reflects itself in the far field. Okay. Let me remind you. Yes, sure. So there's more than one case. There's the case of a freely moving object. So there are two or three sort of disclaimers. One is really this is a problem. This is really a StatMech problem. I've got run and tumble swimmers. I've got active Brownian objects in the medium. The stochastic aspect will come in only in an average sense in the form of a collective diffusivity of those objects. We won't solve the actual stochastic PDE problem. Okay. Secondly, you can imagine a situation where the object is allowed to move around and a case where it isn't allowed to move around. And I'll say a little bit about both cases. Now, let me remind you of Stokes hydrodynamics. If V is the velocity field and then the equation for the velocity field, where we completely ignore inertia and unsteadiness, is a balance between viscous and other forces. You can describe the swimmers either as little objects with a force dipole or something on them, or as an object with a surface slip velocity boundary condition, which results in a far field flow corresponding to one of these. Okay, and so in general you'll be solving this equation with prescribed force densities and or prescribed boundary conditions of various sorts. On the inclusion, you can imagine some no slip, no penetration boundary condition. On the swimmers you can either describe as a force dipole or something, or depending on what else you have, maybe you've got a sedimenting particle, in which case it's a force monopole. Or you can describe the swimmers as themselves having, as I said, a slip velocity boundary condition on their surface. The thing, for those of you who aren't familiar with Stokes hydrodynamics, the important thing to note is this. Let's forget about this detail. So you've got an unbounded viscous fluid and you've got a swimmer in it. If it's a force-free, remember, swimming is a force-free activity. The force the swimmer exerts on the fluid is balanced by the force the fluid exerts on the swimmer, because there's no external force. Newton's third law tells you those forces are zero. So if you describe the swimmer by a force density, if you write down the equation for the joint velocity field of swimmers plus fluid, the force in that is zero. Therefore, any force density you ascribe to it can't have a monopole moment. Right? So a force-free swimmer will have a force density which is a force dipole. If the force density has a monopole, for example, in the case of a sedimenting particle, the velocity field will decay as 1 over r away from that object. This is all in 3 dimensions. And if it's a force dipole, it will decay as 1 over r squared. You don't really need to know much more about this, but you'll have to keep both of these in mind, because although we're talking about swimmers, depending on the type of inclusion, a monopole aspect can come in somewhere. Okay, so the background to this problem was that this group of people a few years ago had studied the problem of a collection of active Brownian particles, not with any hydrodynamics of the medium, but just a concentration field of particles, so-called dry active matter. So each particle propels itself along a direction described by a unit vector ui with a speed, a fixed speed v0, and in principle in the presence of some kind of material object, in the simplest case described by just a potential. Okay, so you could imagine the potential to be a actual pair interaction between the object and the thing, or it could be maybe some optical trapping potential or something. Mu is the mobility, no inertia, so this is the equation for each particle. The direction of each particle in this very simple model simply does rotational Brownian motion, and so it has a correlation time tau. You can take this problem and build the equation of motion for the number density field of these particles, and what you will get, there's 2 things to note. One is, of course, even if you don't add any noise directly acting on the position coordinate, even if the only noise is the change of direction of u, on long enough time scales, if nothing else is happening, r dot equals u will give you a diffusion. And that diffusivity will be the self-propelling speed squared times the persistence time, the correlation time of the direction. What you can do with a little bit of algebra, which Yariv and company did, was to show that in the steady state, the number density field rho of these active particles obeys an equation with 3 bits to it. Diffusion, pushing around by the potential that represents the inclusion, and some details representing the near field on this object, which are really important. Okay? And the result of this is that the far field density has, now remember, supposing this was particles at equilibrium in a potential, you just have diffusion and the interaction of the potential, and the density with these 2 pieces would decay, these are non-interacting particles, would decay exponentially would decay as e to the minus the potential over kT, right? That's all that would happen. The result of this activity is this additional piece. You get a 1 over r squared decay of the concentration governed by a coefficient which is really the mean force exerted by the inclusion of the active particles. If this was thermal equilibrium, that mean force would have to be 0. Okay? And because it's not, you get this interesting decay. So this was a nice problem that these guys solved. They've done many things with it since, including pointing out that it leads to long-range interactions between two. If you have two objects in this active bath, the active bath mediates long-range interactions between those objects. If you have a disordered boundary, it can even dramatically change phase separation in the bulk and so forth. So many nice things have come out of this problem. Yes? Yeah.
Just tweak the local bias at a very diffusion rate small and just a localized bias. That can induce.
No, but what does a localized bias mean? You're driving the particle in some direction. Is it a driven problem or not?
No, you just say that okay. I mean, you can go from let's say x to x plus 1 with some probability and opposite.
But that's driving, isn't it?
Essentially, it creates a dipole.
No, I know, but I'm saying that that's not an equilibrium problem.
No, it's not equilibrium.
Yeah, that's what I'm saying. So I was just giving you.
Neither is active bath equilibrium problem.
Sure, I'm saying there's a variety. When you've got a conserved field, almost any kind of out of equilibrium imposition tends to have long-range effects. The fact that you have a conservation law, but you don't get a power law decay, is because of the conspiracy called thermal equilibrium. So many different ways of breaking it result generically in power laws. This is an example. Yeah, I totally agree. Now the thing is, let's take the same problem, but replace, think of these particles now as active swimmers. So then what will happen, you can repeat the analysis. First of all, you can sort of intuitively see that essentially what will happen is that your particles will be moved around by the hydrodynamic velocity field of the fluid and by the force exerted by these guys. So really, I can do a large amount of algebra, which I will not do. The density will obey this equation. The question is, what is V? Okay. And the important thing is the following. So I'm skipping many steps, but what's really crucial is the following. So you've got a medium. That medium is being actively forced by a bunch of swimmers. So as far as the medium goes, it's really a fluid with a colored noise in it, with a colored momentum-conserving force density in it. Okay, with no spatial correlations and some finite time correlation. That's about all. But the important thing is if you stick an object into that medium, supposing I take that medium and I take an object that looks like this. Notice this clicker is a polar object. If I take this object and put it into that active medium, it will become a swimmer. That is, the generic interaction of an active bath in a momentum-conserving fluid with this object will propel it. Therefore, if I don't want it to propel, I have to hold it. If I hold it, it is now a force monopole. Okay. So the force monopole that I'm interested in here is the one that results from taking my inclusion of polar shape and grabbing hold of it with a light field, for example, right? So the point is, supposing this is my trapping potential, the reason it's a force monopole is that my particle is trying to move, so it'll get trapped somewhere here, not here. So it'll get trapped at a place where there's in effect, you are taking the system and creating a force monopole in it in order to hold it. Okay, so that is the problem that we're looking at. Okay, and clearly, whatever else happens, this object is going to produce a fluid flow of this form. Okay, so the problem you'll be solving in the far field is this. Okay, far away from the potential is unimportant. What you've got is the fluid flow generated by that object, and you've got this localized source term, which, if you're far away, is some vector dotted into grad delta of r. Okay, and the two cases that you have to keep in mind are of a polar inclusion, in which case the velocity field decays as r to the minus chi with chi equal to 1, or an apolar inclusion, in which case you don't need to hold on to it by a force, okay? In which case the decay is as 1 over r squared. So under r going to minus r, this term will pick up a b to the minus, r going to b r, sorry, this term will pick up a b to the minus 2, and this term will pick up a b to the minus 1 minus chi. So if chi is bigger than 1, the advection doesn't matter. If chi is equal to 1, that is, if it's a polar inclusion, these two terms rescale the same way. So advection is marginal. Okay, so that's the problem we are interested in solving. Okay, and on general dimensional grounds, you might think that, look, you know, all I've got this source strength, and I've got diffusivity, and delta rho should just be 1 over r squared times the source strength over diffusivity times some function of direction. In general, however, since I've got a material inclusion of a certain scale, in principle, you have to allow for one more dimensionless combination, namely a length scale associated with the inclusion divided by r. So the general dimensional analysis expression is this. I'll tell you what happens if you try to ignore this. If you write this object down, expand it in angular Fourier series, in case the object has a non-axis symmetry, it turns out you do have to allow for this function to have a dependence on this inner scale over r. You can take this expression, you can go back to this equation, try to write down an expression of this form without the L over R to some unknown power. And what you will find, with a little bit of algebra, is that this function then blows up at cos theta equals plus or minus 1. So the point is, the naive dimensional analysis without the anomalous scaling fails in general. So then you take this problem, and what's the important parameter? The important parameter is how polar is this inclusion that you stuck into the medium. So there's a non-dimensional combination associated with, so this is a kind of Peclet number. Okay, you've got an object in the medium which is forcing the medium, and it's just a comparison between that and how quickly the medium is rearranging itself and uniformizing itself. So that's the important perturbation parameter, and you have to do a bunch of algebra on this equation. And for each angular Fourier component m, there's a decay exponent epsilon m. Perturbatively in lambda, what you have is the m equals 0 bit, which is plus something times lambda squared, and the m equals plus minus 1 bits, which is minus something times lambda squared. The angular dependence is governed by the same parameter lambda in this somewhat elaborate way. So you can, so this, the sense, I mean, this is the essential physics of this problem lies in the fact that you can't ignore the inner scale associated with the inclusion. That's what gives you spatial dependence not rationalizable by naive power counting. Okay, and you can work these out. You get these two behaviors. So what does that mean? What that means, so let's see which of these applies to which case. If you have a general inclusion with a polarity and no axis of symmetry, then the m equals plus minus 1 modes will matter. The decay will be as 1 over r to the minus 2 plus this, that is 2 minus this guy. The special case of a polar axisymmetric inclusion is one in which the amplitudes of the m equals plus minus 1 modes by axisymmetry are 0. And so you get a decay that's 1 over r to the 2 plus a certain quantity. So these are the two things that one has been able to calculate for this problem. Okay? So, maybe I've under-described the problem. You see what I'm saying, right? I mean, I have an equation whose r theta phi dependence I have to calculate. I do so perturbatively in this Peclet number. At that level of analysis, the only bits that matter are the m equals 0 and m equals plus minus 1. They contributed order lambda squared, and you get this decay. The interesting thing is that the far field decay for a general polar obstacle is slower than 1 over r squared, and for a polar axisymmetric inclusion is faster than 1 over r squared. So, I mean, I don't know how practically relevant it turns out to be, but it's rather interesting that you've got an obstacle far away there. And if you make measurements on the concentration field here, you get signatures of the asymmetry of that object, which is rather sweet, I think. Whether you can use it for sensing or signaling or whatever, I don't know. Okay. So that's the first part. I'll briefly tell you a second part. Supposing you have two inclusions. Any question? Huh.
Equilibrium calculations, you get some complicated laws when you read exponential, you make some argument that if
No, okay, let me tell you. There are two ways of doing this calculation. One is this thing that I just sketchily described. The other is you can promote this to a kind of RG. Yeah. So in an infinitely long appendix to the paper, we also have that. Yeah. So it's exactly how you were saying. And maybe for some people, that's actually a more natural way to think about it.
it's just in some text.
Yeah. So another fun thing you can do is you can now imagine two such inclusions, okay? And let's say they're both polar, and let's hold them both fixed, okay? And let's say you hold their positions fixed, but don't pin their orientations. So then what will happen is each of these guys will produce a fluid flow. And that fluid flow will reorient the other guy, okay? Each of these guys has a polarity, which is basically a unit vector governed by the force required to hold it fixed. Let's say for this guy, it's F2 over mod F2. For this guy, it's F1 over mod F1. So where F1 and F2 are the forces required to keep these guys from swimming away, okay? So you can then write down equations of motion. I won't explain in any detail. The key point to take away from this slide is the following. When normally when you think of objects, orientable objects in a fluid, they rotate because of velocity gradients. When you think of something like a weather vane on top of a building, it rotates because of the velocity, because there is an absolute frame of reference, namely the ground, with respect to which, if you've got an object stuck on top of a building and allowed to rotate, what it tells you is it's true that implicitly it's a velocity gradient because it's a gradient with respect to the ground, but whatever it is. In a two-dimensional picture, it's just the velocity itself. This is something that comes up in some work we did some years ago on flocking of a bunch of motile objects in the midst of beads, where the interaction between the flow and the orientation is not the velocity gradient, but just the velocity. We call it the weathercock or weather vane effect. So therefore, each guy rotates. I mean, these cross products are just because of, I'm saying these are just kinematic ways of describing how P1 rotates, okay? The flow that makes it rotate is the force monopole flow due to each one, because both of these guys are anchored. It's quite a strong effect. The other point is the following. The way a given object rotates in response to a flow depends on its structure. So you can imagine two objects, one of which likes to point in the direction of the flow, the other of which likes to point against the flow. You can have contrary types of rotation. So if you have two rotors in which the signs of these coefficients gamma 1, gamma 2 are opposite, you can get a rather baroque kind of couple dynamics. I'm not sure again what it's good for, but it's at least an interesting toy. Okay, so you could imagine dressing this up to have arrays of these objects. We've not done this yet. Okay, so I'll end. So I've told you about an interesting setting in which marginality and continuously varying exponents arise, and in a context with this lovely thing called intermediate asymptotics. It's rather interesting that the decay of the concentration field is qualitatively different for this axisymmetric and non-axisymmetric cases. In one case, the decay is faster, in the other case, it's slower compared to the case without hydrodynamic flow. And the decay exponent is telling you something about the polarity of the inclusion. So, you can sort of read the inclusion from far away, which is rather interesting. So, so I hope this story was diverting as a first talk of the morning, and you can read more about it there. Happy to answer questions.
Thank you.
It's on now.
No, I mean, in the second case, when the object can, let's say, move around, so in that case also the exponent does depend on the rotation.
So when the object moves around, so objects that can move around or objects where polarity both end up having a decay, this is same as in the dry case. Details will differ, but the power law is 1 over r squared in those cases. So really the only case that's really singularly interesting is the polar obstacle, which you have to grab hold of. So you create a force monopole not by having a particle settling through it, but by thwarting the swimming of a particle by grabbing hold of it, which forces you to exert a force on it, on the system. So it's a static force monopole.
Understand the model. So initially you had the active Brownian particles in a potential. The potential is from the inclusion, right?
The inclusion,
So it's just like a hard wall.
It could be a hard wall, it could be other things, yeah.
Okay,
You could
so-
imagine doing more complicated things.
Right. Yeah. So I mean, in principle, one could write an equation for, like you wrote an equation for the density, which just depends on position. But in principle, I could start with the distribution of position and the orientation, right?
Right.
And then integrate out the orientation, and that's what gives you the divergence of J. Right?
See, it's only from that till you get an effective diffusivity with a single particle, for example, right?
Right. Yeah. But that probably involves some approximations, right? Like.
I mean, at this level, it doesn't because the particles don't have any structure other than they carry an orientation. So yeah, so there will be
because
there's probably a closure at some level. Yeah.
Okay, but I mean, if one wanted to solve the full distribution equation, like it's the boundary conditions would be.
No, so the point is here we've assumed that the obstacle does nothing to the orientation.
Oh, okay, so
right, so that's the easy case. You could imagine having anchoring boundary conditions, or so this is without that. So each particle's orientation does its rotational Brownian motion, even if it's up against the wall.
Okay.
Clearly, aligning boundary conditions at the walls, all those things would make the problem richer, and this is without that.
Okay.
So the orientation is sort of autonomous.
Inclusion also has some shape, right?
So that shape is reflected in the potential V of R. Right?
But then if that inclusion can also move, then V of R changes.
So if the inclusion can...
Money rotates, so it's direct, it's some asymmetry.
So the point is, in that analysis at the end, it's assumed that that is on much slower time scales. So that is also, that is an approximation in the calculation. So it's done sort of, you assume those time scales are separated. You sort of imagine a big object turning slowly. But yeah, it's important that it's been done in a picture where the medium kind of relaxes. Yeah.
Any more questions? Maybe I can ask a fast one. Because in the first part, in the dry case, you mentioned that by putting randomness in the boundary, you change bulk phases. So can you say something about what's happened there, and if you...
Yeah, so that's not a calculation that we did. So Yarif Kafri and company, so it's, okay, so that's actually a little difficult calculation to explain on the board here. The point is, it turns out that, all I can say is that supposing you have a bulk phase separating problem of active particles, let us say undergoing MIPS, and you have a quench disorder at the boundary, its effect can penetrate into the bulk and make the interface of the phase separated region so wandering that in effect phase separation of the bulk is wiped out. But the specific reason for which it happens, it would require sort of a little seminar.
Okay.
Yeah.
So for the swimmer case...
We have not thought about that problem yet. This is really the first thing we've done.
Okay, if there is, or there are no more questions, let's thank the speaker again.
I'd like to thank the organizers for giving me opportunity to speak in this wonderful meeting. Actually, there are two reasons I have chosen this topic. And first one is a bit superficial. Okay, I wanted to have something to do with this title, and I think I have managed to get almost all of it. It's an out of equilibrium system, although I have not mentioned it explicitly, so I think I have managed to get almost 100% of the title. The second reason is, okay, I mean, it's the main reason. Since this is a meeting which is celebrating this Indo-French collaboration, so I thought I will showcase some work which actually came out of this collaboration. And these collaborators are Satya and Manas, both are there in the audience. They're also organizers and also the PIs of this project. So this is resulted in two publications. The first one is about this classical problem with Satya, and then second one is about this quantum problem, which is with Satya and Manas, and it should come out soon, I guess, either this year or next year. Okay. So let's start with a problem which all know, like equilibrium systems. So in equilibrium system, it's described by this energy functional. So this configurations is defined by some these coordinates. So you can just think of it as like a position of a gas particle in a gas. Okay. So this potential, this energy function has a like confining potential, single particle term, two body interaction, three body interaction, and you can put anything you want. Okay. But irrespective of whatever the energy functional, you know that the equilibrium probability distribution for the joint probability distribution of these coordinates is given by this Boltzmann distribution. Okay. And given this distribution, one is usually interested in calculating various micro and macro observables. For example, you might want to ask what is the average density profile of the gas. Okay. What are the correlations? That's something people are interested in. And nowadays, there's also interest finding out these extremal properties. Like, for example, you can ask, there's this gas, what is the age fluctuations? Okay, so you can ask, okay, what is the fluctuation of the rightmost particle in the gas? Okay, and in general, you can ask about order statistics. For example, if you ask the kth particle from the right, what are the statistics of this particle? People are interested in gap statistics. So again, you can ask what is the distribution of the gap between, let's say, kth and the k plus 1th particle, and full counting statistics. So it's basically the statistics of number of particles in a given region. And you can take this region for simplicity to be minus L and plus L, but you can generalize to anything. Okay. So these are some of the observables interested, but you can ask, I mean, you can consider any other observables. Okay. So if the system is non-interacting, where your two body or any higher body interactions are not present, then this joint distribution is of course very trivial. So it has this product measure where it factorizes into single particle distributions, and where the single particle distribution is basically the single particle Boltzmann distribution. So in this case, these variables are IID random variables. And for this ideal gas, all these observables which I have mentioned above, these can be calculated very easily. Okay, these are like a very simple questions. Okay, but if you have interaction presence in the problem, okay, although you know this joint distribution, which is a Gibbs distribution, the computation of this observable is usually rather hard. And when I say interacting, I mean strongly interacting system. Okay. So except one case where many of these observables can be computed, although the calculations are quite hard usually. So this is called the so-called rich gas, and I think somebody mentioned it already. I think Kiran, you did probably, yeah. during this conference. Okay. So these cases, basically many of these observables can be computed explicitly, and many of these people in this audience actually are involved in calculation of this observable, like Abhishek, Manas, Anupam, Satya, Gregory, and many of their collaborators. Okay. So this is one example of strongly interacting systems where you can calculate this observable, but these kind of examples are rather rare actually. Okay. If you go to non-equilibrium system, it's even harder because you don't even know often how to calculate this joint distribution. And unlike this equilibrium, this joint distribution is not a priori given. And in some cases, even if you know the joint distribution, this calculation of these kind of observables are rather difficult. Okay, because there is no general prescription for doing this kind of calculation. Okay, so if you go to the quantum domain, again there are very few examples where you can do exact analytical calculations. For example, nowadays people are interested in interacting bosons because they can be realized in cold atom experiments, and usually these people use this model. We have already heard about this Liebler model where these bosons, they are in one-dimensional this thing and they interact via this delta function potential. So in this case, okay, you know the solution for the free case, it can be written in form of Bethe answers, but if you put a potential, it breaks the integrability. So for any experimentally relevant situation where usually you have a optical trap, so this doesn't work. Okay, so you don't know the answer. So similarly, when this Gross-Petersky equation, where again it describes this weakly interacting Bose gas, so if you put a potential, these analytical solutions are very difficult. So all these experimentally realizable situations where you usually have an optical trap where your system is there, they are very, it's very hard to do, very hard to find a model where you can do analytical calculations. Okay, so the moral of the story is that, okay, so there is a possibility of analytically tractable model for strongly correlated gases in both classical and quantum regimes. Okay, and even if a solution can be found in some cases like this Liebler model without the potential, this analytical calculation of this observable kind of observable I mentioned, it's usually rather hard. Okay, so there's a growing need to engineer analytically tractable models for correlated gases, and when I say correlated gases, means strongly correlated gases, both in quantum and the classical domain, where you can do calculation and also these are experimentally feasible. Okay, so before I talk about engineering these systems, so let's just ask this question: like, I mean, why are non-interacting systems are easy to deal with? And answer is very simple, because in a non-interacting system, the joint probability distribution is, you can write as a product of this individual probability distribution. So it has this factorized form, and this factorized form, which is this IID form, basically, which makes analytical calculation easy. Okay, so then question is, can we engineer a correlated gas, strongly correlated gas, that retains this product structure somehow? Okay, so it might sound contradictory, self-contradictory, because if I say that, okay, if you have this product structure, it is non-interacting, but then I want to build a strongly interacting system keeping this product structure, right? But the answer is actually yes, you can do that, and answer is this one. Okay, so of course I can write down a joint distribution of this form. Okay, so I can write down, I have a product structure, something there, and this is characterized by some parameter u, okay, and I average over this parameter u, okay, and this p can be anything, okay. So I can just write down by hand, but that's not the point, right? Can I realize a system which has this product structure? So can I have a system which I can realize experimentally or physically, which gives this product structure? And this is this structure. There is a class of model recently it is found. So this structure is called this CIID structure, conditionally IID structure. Basically, you have a IID structure inside, conditioned to some parameter u, and you average over u. Okay. So it turns out that you can actually find this kind of structure by physically realizable models. And this first model was this a model of resetting Brownian motion. So we have already heard, I think, 2 or 3 talks about resetting Brownian motion. But here, instead of one particle, what you do is that you have large number of particles, n particles, and it let them evolve independently. But then when you reset them all together at the same time. So you simultaneously reset them. Okay? And then again they'll evolve independently and you simultaneously reset them. So this simultaneously resetting process creates a strong correlations among these particles. And that results in this structure, particular CID structure, where this H of U is given by this and this P of X is given by this form. And this is a work done by Satya and Gregory and their collaborators. Okay? So there is a second example. So where again you take this large number of Brownian particle in a harmonic potential. So these are non-interacting Brownian particles. So if you just don't do anything, the system has a product measure. So now what you do is that the strength of the trap, you basically change between 2 values mu1 and mu2, and the time, okay, it's there at some mu1 and then you take a time drawn from an exponential distribution and then shift to mu2 and then let it be there for a time tau that's drawn from an exponential distribution and shift it to mu1. And you basically keep shifting between mu1 and mu2, and this again, this simultaneous drive, okay, creates a product structure, creates a CID structure which looks like that, and where this HU and this PU, these are given by that. So this, in the first problem, actually this structure was almost evident immediately, but the second problem, it was in fact a very hard calculation. This is a problem, this Manas, Satya, Gregory and this Marco Biroli, they did. So this structure was not immediately evident, in fact. So it actually came in a very roundabout way. I think finally they found some integral representation of some Kumar function or some such thing, but it's not evident that, okay, finally this, okay, it's evident that, okay, there will be some correlation, this will generate some correlations, but whether it will result in a structure like that, that was not evident at all. Okay? So therefore, what are the necessary and sufficient conditions to have a structure like that? So you can have a strongly correlated system, but you can have a very complicated joint distribution, then it's very difficult to do calculation. Okay? So the point is that what kind of driving gives rise to this kind of structure? Okay? So answer is, okay, we have some understanding, but we don't have a full understanding. So therefore, it's good to study models where you can see that, okay, this structure emerges basically. Okay? So this is what we did basically in this work, and in this work means basically I'm referring to these 2 publications. So we find 2 experimentally feasible systems, one in the classical domain and other in the quantum domain. So where again a common and simultaneous drive drive the system to this kind of structure, and it generates correlation dynamically among these particles. So dynamically in the sense that if you don't do the drive, this is a completely non-interacting system. Because of this drive, it generates this correlation. So these are dynamically generated correlations. Okay? And in both cases, the joint distribution had this CIID structure. Again, if I remind you, CIID means that, okay, it's like an IID structure inside an integral with respect to some parameter u, and then you average with respect to this parameter h of u. Okay? And this h of u, okay, it depends on what kind of model you are looking at this. But the point is that if you have a structure like that, you can calculate many of these observables very easily. Or you can actually, this becomes an analytically tractable problem. So this adds to a box of problems, basically of systems, of strongly correlated system where you can do analytical calculations. Okay? The first problem is the classical problem. So what we do is that you take a harmonic trap and you put large number of classical particles, Brownian particles. Okay? These are non-interacting particles. So if you just keep the trap, you know that the joint distribution is just factorization to single particle distribution, and you know that, okay, if you leave a Brownian particle in a harmonic trap, it's a Ornstein-Uhlenbeck process, so it will basically reach a steady state. So joint distribution is basically a product of this steady state Ornstein-Uhlenbeck process. But now what you do, you shake the trap. Okay? So where all these particles are there, and what I mean by shaking the trap is that you take the position of the trap and you basically, the position of the trap undergoes a stochastic process. Okay, so this is basically your energy function, and for each particle, this is the dynamics, where z of t is the position of the trap, and the z of t undergoes another independent dynamics, stochastic dynamics. And so for the time being, that this stochastic dynamics can be anything, but if you want a steady state, basically, okay, you should have a system where z of t always remains of the order 1. Basically, it doesn't grow with time. So in this case, you can again find out the joint distribution explicitly at any time, in fact, and which has this form where this P is given by this, and this H of u is the probability density function of this variable u, which has this dynamics. Okay, so u has a distinct process, and the z of t is still arbitrary at this point, basically. Okay, it can be any process, and if z of t remain of order 1, in that case, in the limit t going to infinity, it reaches a steady state, and where the steady state is given by this. Okay, so where this is this IID thing, and this h of u is the steady state distribution of this process. Okay, so I want to note you that you might think that, okay, I have this trap, and this, okay, trap center is z of t, and okay, this particle is basically concentrated around the center z of t. But you should know that this is not the z here. It's another variable u. It's an auxiliary variable u, which is coming out of this another stochastic process, basically. Okay, so it's not x minus z. It's some Gaussian around x minus z. That's what you would have imagined. Okay, if you do some adiabatic thing or something like that. Okay, you can, given this structure, of course, you can also compute the correlation very easily. And what you find is that, okay, you have a positive correlation for all-to-all particles. So you have an all-to-all particle correlation. Okay, so a representative example, you can have a telegraphic noise. For example, you can have a trap which just moves between two positions, like it just keeps going like that, and the time between this thing is drawn from an exponential distribution. So this trap, this equation in that case is basically the same of a run and tumble particle in a harmonic oscillator, and you know the steady state this thing. So this is the h of u for this process. You can also take this z to be an unstable process. Then in that case, the steady state of h of u is given by that. But you can take your favorite example for z of u, and it will generate a new h of u, basically, right? The point is that for any h of u, basically, we have a structure which is given by this. Okay. The second problem is a quantum problem. So where what we do, so you have a harmonic potential centered at x equal to plus a, and you have large number of non-interacting bosons. Okay, so these are non-interacting, and you cool the system so that they are in a ground state. So we start with a ground state of this Hamiltonian. So this Hamiltonian is basically the Hamiltonian of these particles in this potential, and you cool it to the ground state. So now what you do, you instantaneously you shift the Hamiltonian from here to here. Okay, you quench the Hamiltonian from here to here. That's equivalent to basically moving the trap center from minus a to plus a to minus a. So you just change the trap center, and let the system evolve unitarily. Okay, this is a unitary evolution. The time for which you want the system to evolve, that's a random variable, and that you draw from this exponential distribution. And at the end of this time, you reset this wave function to the ground state of this potential. So this is, you can think of it like in experimentally, basically you shift the trap center to again plus a, and cool the system to the ground state, and you assume that, okay, the time taken to cool the system is basically negligible in compared to the experiment. And then you just keep repeating this. So you put it here, cool it there, and then move the trap there, let it evolve unitarily and for some time tau, and then you again quench to the ground state, and you keep doing that. And this repeated quenching to the this Hamiltonian and then resetting to this ground state drive the system into a non-equilibrium steady state. And in this non-equilibrium steady state, basically, if you look at, so how does it work? So if you basically you have this unitary evolution during this time tau, which is drawn from exponential distribution. And for this time, okay, you can write down this density matrix. And as in the classical stochastic resetting, here also you can write down actually evolution of density matrix in the presence of resettings. This is the work done by Christian Du, Satya sometimes back. And then once you have this, you can write down the quantum joint probability density by this just this matrix element basically. It's just the diagonal term of the density. And what we find is that in the time t going to infinity limit for this system also, this joint distribution goes to a steady state where the steady state distribution is given by that. Okay, so where okay sigma is this guy and this h of u is given by this. Okay, it looks a bit complicated, but okay, you can explicitly find basically. You can find the correlation function again and see that these are positively correlated and these are all-to-all correlations. So I'm keeping this thing, okay, this logo basically whenever I put this one, you should understand that I'm talking about the quantum problem, and if I put this other diagram, this is about the classical problem basically. Okay. So to summarize, basically we have engineered two systems, one is classical and one is quantum. And by this simultaneous driving and this driving protocols are different in these two cases, but in this driving you can basically drive the system to a steady state, and where the steady state has this CIID structure. And given this structure, you can of course compute many of these observables. Okay. For example, you might be interested in average density profile. Okay. So how does the density profile of the gas looks? Okay. So this is simply given by that. This h of u depends on the problem. For example, in this classical case, this logo means the classical case. So let's consider driving where this z of t is a dichotomous process. Basically, it just varies between two values. So you just trap center is just it can just takes two values basically. You just keep shifting the two. So in this case, you see that actually this density profile shows very interesting behavior. In fact, we can have a phase space where there is an active phase where this density profile has these two bumps kind of thing, or you have a passive phase depending on this parameter where it has a bell-shaped curve, and then this is the one in the boundary. So you can find that okay, basically this second derivative vanishes this thing, and then you have to go to the third one. Okay, this is the quantum case again, depending on okay either you fix sigma, which or change the resetting rate, or fix resetting rate and vary sigma, and you see that it has a rather nice transition from a single bump to a double bump structure basically. Okay. Order statistics again. So you can find this order statistics for, as I said that, okay, so if you have this position of this particle, and order means that, okay, M1 means the rightmost particle, M2 means the next one, and so on. So if you just so these are the ordered positions. So you can ask what is the distribution of this kth maxima. So in general, for any kth maxima, what we find is that the distribution is given by this H itself. Okay. So to contrast it, you remember that okay, for a IID random variable case, the distribution of the maximum goes to one of the three well-known distribution, either Fréchet, Gumbel, or Weibull. But this distribution is very different from those distributions. So this is a strongly correlated system indicating. So where this Lk is basically given by this, where alpha is basically k by n when it is in the bulk, and this is at the edges basically. Okay. So these are some examples. This is again this dichotomous noise. So you see that this order statistics for any k, when you scale it, they all collapse to, so this different alpha mean basically different k. Right. So they all collapse to nicely this one, these three curves in these three regimes of this new. Okay. Order statistics for bosons, again, you see that okay, it's basically okay, it's all collapse to a nice curve, and this is basically yeah, simulation versus the theory. Okay. Gap statistics, again, we find that the gap statistics is an exponential distribution where this characteristic length ln or characteristic gap can be explicitly calculated. Okay. So again, you see that okay, this is for a large number of parameters both in the quantum and the classical cases, they nicely collapse to this exponential distribution. Okay. Full counting statistics, finally, so we are asking the distribution of the number of particles in a region minus NL plus L, So we find that it has this scaling form. So NL by N is the fraction of particle within that box. So this kappa in general can be between 0 and 1 because this is a fraction of particle. But interestingly, what we find is that there is a upper bound kappa max which is strictly less than 1. Okay? So you cannot put all the particles within that region basically. It's almost like some strong repulsion, and it has a square root divergence at that point. Okay? So these are some representative examples. So this is the classical case. So where this is the dichotomous noise case, and so that this is a square root divergence here. So in this case, actually, when the kappa mean has a bound which is not strictly greater than 0, but if you have a Ornstein-Uhlenbeck drive, so kappa mean is 0. Okay, I'm just done actually. And then on the other hand, the right side is always a kappa max is actually strictly greater than 1. So full counting statistics of actually bosons is very interesting because it has this two pieces structure. Okay, so first of all, kappa max is always strictly less than 1. That's a generic thing. And kappa mean is also strictly greater than 0, but it's very close to 0 so that you don't see it. But what you see is that, okay, it has a square root divergence here, it has a square root divergence here. But this one, this is a discontinuity. On the, if you come to from the right side, it fixes to a constant value, but on the left side, but if you go from this side, it has a square root divergence. Okay. So to conclusion, basically we have engineered two strongly correlated gases where correlation between non-interacting particles emerges dynamically, and we have a joint distribution of this thing which has this CID structure, and this structure allows the calculation of many of these observable explicitly. And I was talking about, this engineering and experimentally feasible thing, but can one actually do experiments on this? And so this is something actually at my colleagues at RRI, they are doing it at, and they actually can do this in this cold atom system, and you see that, these are still preliminary data, but you see this, you have a single bump versus this double bump depending on how you shake that. Thank you for your attention.
Thank you, Sanjeev.
So in your final conclusion slide, you have this product form integral with du. But can one do a functional integral over u of t? That will be slight generalization of this. You know, there is a control parameter u of t which varies with time. And now you do functional integral over the probability of that particular profile.
Yes.
Does that extend this analysis somewhat, or is it identical?
It does in some sense. I don't know whether you meant this one, but in the classical case at least. So yeah, in this case at least this u is also a time dependent variable, and we can find it at full time. But this is still a single time property. I guess what you are asking is that basically like a functional of the time, and yeah, in this case, probably one can do it actually.
Okay,
yeah.
Thank you.
But yeah, it's like a full path integral.
So in the quantum case, if you do the same thing you did classically, that's
we are doing actually. That's a bit harder problem. Actually, we started with that one.
Okay.
Right, and so then this this protocol turned out to be simpler than that, but that one we are doing basically whatever the same thing we are doing classically, you also do it in a quantum. You can write down the equations actually. So we have the equation,
but it's not clear if it will have this structure.
So that we don't know yet, but so what we know is that this for any time it remains Gaussian. So that's why you can do that, because the propagator is Gaussian, right, in a harmonic potential. But then this soon this the whatever the shift and this thing, it becomes more complicated basically. Like it's a Gaussian with around some mean, and then this mean, how it evolves with time, it becomes a bit complicated. That's what we actually started with that problem. Yes.
Is it working?
Hi, Sanjeev. So this quantum problem of the quench of the harmonic trap. So the quench and resetting and back and forth, can I think of that as a sequence of instantaneous quenches starting from the ground state of a harmonic trap?
Yeah. So what we are doing is basically you start with a ground state of a different harmonic trap.
Yes.
And you are evolving in a different harmonic trap. So you quench to the ground state of this harmonic trap.
Right.
And then you evolve on that red harmonic trap basically.
But the reset also, I can think of that as a second quench or not?
It is a second quench. It is a second quench.
So now my question is that, you are starting with a free system, right?
Yes.
So if I think of this as a quantum field theory,
Yes.
I seem to remember that in a quantum field theory, even if you do a sequence of quenches, Wick's theorem remains true.
Here, when you do, you quench, then you cool down the system. That's cooling down the system is not a unitary operation, right? So it's not only quench. So when I say resetting to this ground state, see, because otherwise, if you take it there, put it there, evolve, and then you bring it here, the system will not come to the ground state. To bring it to the ground state, it has to be an open system.
I see.
And that is not a unitary operation, and that these people in the this cold atom community, they can do, and they can actually cool down pretty fast. So in principle, you should actually take into account the time of cooling, and that one can actually extend it.
So I see. So you're coupling to some external system,
You're coupling
and you are
to some
integrating that
system.
out. As a result, some interaction is
Exactly.
coming in.
You're coupling. So this resetting part is basically quenching to this trap, and then coupling to some outside wall, and then you bringing the system to the ground state basically.
Yes. Okay.
Yes.
Thank you.
Yes.
Question? So I think, no, maybe one. Let's take the last one.
Actually, you just mentioned it, this time. So, you can imagine that they take some time to come.
Yes.
Like imagine you turned a very sharp trap on, so then everybody went down to the...
Yes.
So if you take that, you'd still get this structure?
So we have not done, we basically in this calculation we have assumed that time to be 0, right?
Yeah.
But I think one can take this to account the similar way people do in the classical stochastic resetting, right? You assume that, okay, I think, I forgot now who, there is calculation where you reset and then there is some time you wait before the system evolve, right? And that time again you can draw from some another random variable basically. So you assume that, okay, you quench here after time tau, you quench here, and then there is another time tau 1, let's say, involved to bringing down the system to the ground state, right? And that time again you can take it to be a stochastic variable with some distribution, and I think one can probably do the calculation, and I believe that this structure will remain. But okay,
both in classical and quantum.
I think both in classical, but I have not done the calculation.
And the only constraint is that they should all land there simultaneously.
I mean, it doesn't actually land there, right? Because in this case...
I mean, in the classical case, everybody goes to...
It doesn't go, actually, because classical case, I'm just shaking the thing, right? So it doesn't go there.
Okay.
So there is no resetting. I'm just, classical case is even simpler. So because it's very easy for the experimentalist. I have this trap, I have this n particle, and I'm just shaking the trap, that's all. It's like this thing villages people used to do, no? You have this grain and then you just shake them, and it's as simple as that, basically.
Okay. Thank you.
Yes.
Okay, so I think we can thank Sanjeev again. Okay, so the third and last speaker of this session is Nicolas Laflorency, who will tell us about a new perspective on MBL.
Okay, thank you, Valentina. Thank you, all of you, to be here this last day. Thanks a lot to organizers. It's very great for me to be here, my first time in India. So you see, just bought that yesterday in the city. I think this is my last talk with the Université Paul Sabatier because it will disappear. It will be replaced by University of Toulouse, January 1st. The bigger thing. Okay, so this is the title of my talk, so I will try. So this is a bit of the follow-up after Fabien's talk on Monday about basically the same model. And so we will revisit many-body localization using simple objects, which are these spin correlation functions. So this is a joint work with Fabien, of course, and also Jeanne Colbois, who did her postdoc with us in Toulouse in the past 2 years, and now she got a permanent position at CNRS in Grenoble. Okay, so this is the outline of the talk. So I will briefly remind what is the status of the MBL problem nowadays. And then I will introduce this very simple object, the correlation functions, and then discuss deeply this object across the many-body localization phase diagram. And with that, we have discovered that the rare events are very, very important, in fact, and so we are going to discuss them as much as possible. So, MBL in one slide. Thank you, Fabien, of course, because he did a half an hour introduction on that. So if you're interested, there are a few interesting big review articles, and I strongly suggest the last one, which is the most up-to-date, and I think this is a very great work. So if you're new in the field, don't be afraid, and you can go to this review article. There are a lot of very, I think, deep and relevant information. So the basic question, of course, back to old days of MBL, is can Anderson localization survive to interaction? And so one of the first answers, of course, was yes. Okay, good examples in this paper, analytical paper, where they show that indeed putting weak interaction at least make Anderson survive. So an insulator, which is called a many-body localized insulator. But in fact, it's also a no. And this is what we recently found in this paper. It's very small, but this is the paper that Fabien discussed at length, that if along the Anderson line, the non-interacting line, if the disorder is not very strong, that means your bare localization length is quite big, and in that situation, you are in a different side, if you wish, as compared to this avalanche criterion, and it could be that weak interaction immediately delocalize your system. So in fact, there are two possible scenarios. So the answer of this question is yes and no. So that's, I think, an important detail to say. So then, what are the main properties of MBL? So here I give a list. Okay, we can class them in two categories: eigenstate property and out of equilibrium property. So for example, eigenstate, they have very low entanglement. They have a spectral statistic which is Poissonian. If you go to Hilbert space, there is genuine multifractality. Okay, and then if you're interested in out of equilibrium properties, there's no thermalization. This is one of the big thing. And for example, there is a memory of the initial, for example, spin or charge pattern that can remain a very, very long time. And if you're interested in entanglement, the growth is extremely slow, ultra slow, like a log logarithmically growing. And among all these, this is mostly numerical observations. And there are only a few analytical developments. One which is very successful is this LBIT model, where, okay, but for me, it's still a sort of phenomenological model. It explains a lot of things, but I think it doesn't explain all of things, all what we observe. So, of course, on that, there are important debates. And here, I cannot resist to show you this, how the estimate of the critical disorder strength for the Heisenberg chain in a random field has evolved along the years. And so you see, in fact, on that scale, of course, you see it goes from 0 to 20. It's okay. This is reasonable, I would say, within error bars, except a few like outliers. And this one, in fact, this blue big error, well, it's not an error, of course. This is like a range of different estimates. It came from the Morning Star and David Hughes paper, well, Colmenares, Kemani, Luiz, and David Hughes paper, where they, in fact, they described what we think to be the MBL regime on finite system as a sort of a series of landmarks where, depending on what you look at, you think to observe MBL transitions. And important, like, thing they observe is this system-wise resonances, okay, that they think to observe around disorder 7, okay? So I will come back later to these numbers, what they mean in our language. And so they say these are some kind of precursor, finite size, of the dominant mechanism of the transition, which is supposed to be avalanche instability. And what they call the avalanche instability come here. And so this is what they expect to be the infinite size phase diagram. So only 2 phases, an ergodic thermal phase and an MBL phase. And so they say what all we see in numerics is some kind of pre-thermal thing, and at the end of the day, everything that will disappear. Okay, I don't fully agree with that, so you will see why. But okay, this paper was quite influential, and so many people believe okay, MBL maybe does not exist. Also, this I'm not this family, but okay. So. There are many ways of tracking MBL, but something which I think was missing is a true real space object to catch possible system-wide resonances. And to do that, there is like a very simple candidate in real space, which is a 2-point correlation function. Okay, so we are going to go with our favorite model, the XXZ, okay, which is supposed to be a standard model for MBL. So this XXZ, this is the spin, in the spin language. You have the, okay, the XY part, which is a non-interacting part, if you want, interactions and disorder. And this, using Jordan-Wigner transformation, for example, can be seen as a fermions hopping, interacting in a random potential. Okay? So this is a quite general model, yet quite simple enough to capture the physics of MBL. And we are going to focus on this 2-point spin-spin correlation function. So these objects, of course, are known for a long time in condensed matter. They are very standard. And so what we generally expect for this problem to capture localization in a localized regime, because, okay, these objects should decay exponentially with some lengths, okay, correlation or localization lengths, as you want to call it. So this is what generally expected in the localized regime. In the delocalized regime, you will see it depends on the what we look at for this object. And there are 2 ways of looking at the correlation. One is like the bulk, like as a function of the separation between the 2 sides, okay? And another possibility is to look at something which has the maximal distance, okay? I will call it the system-wide, a distance L/2 across the chain. And then if you do that, the nice thing is you can just scale your system size, okay? And you have only one length scale in your problem. So also the nice thing with this object is this is experimentally accessible. And there are a few MBL experiments, and in this experiment, they can measure at least the diagonal component, the CZZ, which in terms of fermions or bosons is just the density correlation function. And okay, there are some already preliminary experiments on very small chains, but they can access this object. And surprisingly, if you go to the huge literature on the theory paper about MBL, I could only find 3 where they study this correlation function. Okay, so we thought, okay, maybe we should try to do something on that. So let me try to explain first 2 simple limiting cases what we expect for this correlation function. So in the Anderson localization, which is at 0 interaction, delta equals to 0, this is an example of an exile diagonalization calculation in the middle of the spectrum, okay? So we are supposedly at infinite temperature. And so if you look at the XX or ZZ component of the correlation, you see this is a log, a linear scale. And so this is a beautiful exponential decay. From that, we can extract correlation length, psi. And so here I show how the correlation lengths in the non-interacting regime behave as a function of disorder strength. So you see they both are finite, and they only diverge at zero disorder as expected. So everything here is expected. And there is an interesting relation between the psi x and psi z. Okay, there is a factor of 2. I will not go into the detail. Yes, Satya. Oh, sorry. And in fact, also these correlation lengths are a good proxy for the localization lengths because the one particular localization length is put it here. So you see they behave basically similarly. Okay, so this regime is, in fact, is well understood. Now the other regime, the ergodic regime. Okay, so weak disorder or finite interaction. So here the ergodic regime can be basically a typical eigenstate is like a random vector in the Hilbert space, okay, of this form. So here this is a sum over all my basis states, okay, and all the coefficients can be random inside, but in magnitude they have basically the same order of magnitude, 1 over the Hilbert space size, okay. This is an important thing is the correlations in real space, they will not depend on the distance because I have a random vector. Okay? So there's no this notion of distance. So taking these two in fact, hypotheses for such random state, we will expect the XX correlation to be like this, 2 to the minus L over 2, which is in fact 1 over the square root of the Hilbert space dimension. And if you want the proof of that, this is like a one-line proof, in fact, because you can compute the S plus S minus on such a given state, and you see that you just flip a pair, and so you sandwich with the bra, and so what remains is a sum with random sign, which you pick up a square root of n divided by n, so that gives you the 1 over square root of n. But then if you look at the ZZ component, this is very different. Because here in our XXZ model, we have a conservation, which is the total spin conservation. And so the total spin conservation, that means this correlation, so the sum of these 2-point ZZ correlation function is a constant, and it can be 0. We can work in the subsector 0 magnetization. And taking the fact that, again, the correlation, they don't depend on the distance, all these objects, they are basically the same. And so you have a sum of L squared term, okay, and this one line, you find that this CZZ go like 1 over L, basically. So we have an algebraic versus exponential decay for the correlation. And this can be checked using like numerics on random state, and indeed, the ZZ goes like 1 over L, and the XX goes like exponentially. We can also check then for the true microscopic XXZ model, and this is also indeed what we find, of course, with a few corrections as compared to the exact random state, but still, we have this phenomenology where if you look at the XX correlation function, there is a finite correlation length, and if you look at the ZZ, there is formally an infinite correlation length because this is an algebraic decay. So of course, we expect something interesting to occur across the phase diagram. So this is a point, for example, here in the MBL regime, where we see that both components, they decay exponentially with this hierarchy. It's not exactly a factor of 2 in that case, but there is still psi x, which is larger than psi z. And then if you go to, on the other side, a completely different decay of the correlation function, where psi x remain finite, but psi z is formally infinite. So further we expect an inversion of the dominant correlation across this line and something even more important to happen. And so here I show the correlation lengths, the psi x and the psi z, for such an horizontal cut across the MBL phase diagram. And so what you see first, you see indeed an inversion of the dominant correlation, but more importantly, what we observe, so the blue-green are the ZZ and the red are the XX. Here in this regime, we observe that psi z as a function of different system size, because we take different system size and we extract this local correlation length for increasing L, it's not stable. There is an instability. So the extracted correlation length increase with system size. So this is a sign of some kind of instability. And this is an example of the fit. So you can fit on the first system size, and then you can go to other system size, and we see that there is a drift. So this is clear in this regime. While in a regime where all the other estimates, they show a clear MBL behavior. Okay, so these are the standard estimate, and this is the extrapolation. So this gray line, this is the transition point extrapolated. Okay, so here we are in a regime where normally, if you look at the gap statistics, this is Poisson, without any doubt. While if you look at this correlation function at long distance, they show still some instability. And the instability is also observed beyond the point. Okay, here you see as a function of system size, the correlation is not fine, it's not fixed. It's still growing a bit. So something is happening. And you can do that for all the scans, the possible scan. And so, okay, so it's a bit of French type color phase diagram. But we identify this regime of instability like all here, okay? So these are the extrapolated points that we already found with a standard estimate, and this we have a regime of like quite large instability. So the next question is what this instability regime is. Is it what people call the pre-thermal regime? Does it catch resonances, avalanches? So we are going to try to answer that. So we keep along the Heisenberg line, okay? And we are going to focus on the distributions. Because so far I just show you the typical behavior. Let's look at the distribution of this correlation function. And so first, the bottom line here is the XX correlation function. And so for 4 different points along this line, we see that in fact, almost nothing is happening for the XX correlation function. There is no broadening, and the shape is basically the same, okay? So you cannot recognize there is a phase transition. But if you look at the ZZ, of course, this is very different. Because here, this is the ergodic regime, so there is sort of self-averaging behavior for this correlation. But then when you go to MBL or the instability regime, we have a correlation function when here different colors are for different system size. Huh? So with system size, there is a broadening. Okay, so, and the shape is very different from ergodic to MBL. And more importantly, if you look, for example, at this part of the distribution, this part are large correlations, okay? The largest possible. The largest possible is 1/4. And here it's log scale, so log 1/4, it's here. There are some rare events. And so we want to put our focus here on this rare event. And to do that, we make a very simple change of variable. Instead of looking at just a log of C, we multiply by 4, okay? And you take the log. So if you do that, the big correlations means log of something close to 1, okay? So that means that this object in log scale will spread in a much larger regime. And so these are this large correlation regime here, okay, this gray area. And so using this simple change of variable, what we reveal here is a fat tail for this ZZ correlation function. And so these are rare events. And good thing is to compare to the XX correlation, because the XX, this is on the right for the same disorder value. And here you see it's more like it's shrinking as you increase the system size, and there's no rare event. So the rare event are on the ZZ component. And to do that, okay, to explore more, we can say, okay, there should be a difference between typical and average. So let's do that. Let's compute typical correlation function, average, and look at how the correlation lengths, typical and average, behave. And they behave, of course, very differently. You see, for the XX, nothing really happened. But for the ZZ, so this is the ZZ correlation function that we have already seen before. But this is the average one. And you see, for the average one, the instability is even more visible for the average. And it also asks the question, but is this fit exponential decay? Is it a good description? Doesn't seem to be. So we try to do something else. And in fact, we found that in a broad regime, the average correlation is better fitted by a power law as compared to an exponential decay. So here I show some data, for example, on a semi-log scale, you see that only the strongest disorder is a straight line, which means apparently a good exponential decay, but all the other disorder strengths, which are like 7, 6, and so on, they are not well fitted by an exponential decay. And they are better, here log-log, fitted by some kind of power law, and we could also extract this power law exponent across the regime. So, in fact, this beautiful French phase diagram can be replaced probably better by this one, okay, which is, okay, the ergodic regime has not changed. We have this, this estimate for the transition. And what we have seen looking at this correlation function, that there is a regime, this green part, which has fat tail, okay, when you look at the correlation function. And only you need to go to larger disorder to say, yes, both and typical and average correlation, they decay exponentially. So this red regime looks more conventional MBL, while this one has something more. And these rare events, they seem to be power law distributed. They have all the one ZZ correlation. And we are not looking at short distance correlation, we are looking at system-wide correlation in a background where typical correlation are very short range. So how this related to other works? So there is this very interesting one, different model. This is an Ising model, more like an Imbri model, for you know, by Giulio Biroli, Hartmann, and Marco Tarzia, where, so the numbers don't compare, okay, because this is a different model, but they found that Wigner-Dyson statistics versus Poisson change around here. For us, it changed here, okay? Separate, in fact, the MBL, so there is an intermediate phase where there is a Poisson statistics, but some rare events. So this is a quite different way they use to look at this problem, but they found on the Hilbert space some rare path of possibly delocalization that proliferate and proliferate when you enter to the ergodic regime. So I think, yeah, our phase diagram kind of might agree, correspond to our fat tail regime, correspond to the rare path regime. And if you want to come back to the Morningstar phase diagram with all these landmarks, we don't have strong contradiction with them for the moment, and possibly what they call system-wide resonance, they find it around 7, 8, that compares reasonably well with our estimate. But the avalanche type transition they have seen, we don't see that. So is that the end of the story? No, because in fact, you can even go to larger and larger disorder. And we have seen in very interesting stuff. So this is a simple sketch of what? Of the correlation function across the full spectrum. So what I did, I took 3 samples, and I did the full diagonalization, and you compute for all eigenstate the correlation function. And so you report this as a function of the energy density. So this is the ground state, this is the top state. So here, weak disorder, everything is the same, okay? So you have something which is delocalized. In the middle, 8, okay, you can see some strong fluctuations from sample to sample with some big correlation, but most of them are very small. But if you go to very large disorder, here I pick up 18, okay, so 18, this is very large as compared to my phase diagram. And most of the sample, they show like flat. So flat is 0, and if I go to the log scale, this is how it is. So you see it's like 10 to the minus 4, the maximum. So this means exponential small correlation. But a few samples, this is what they show. Big peak. And you see this peak is at 0.245, very close to the maximal possible value of correlation. And this is weird because we are in a regime of disorder where everything should be like almost a product state. And we have found that, okay, let's go, maybe I should go a bit faster, but okay, so this is the same distribution I showed before, but for a larger broad of disorder strength from 2 to 20. And so you see the fat tail regime start to arrive at 4, 6, 8, but it seems to continue and at some point will disappear. But how to do better? So to do better, we say, okay, let's try to integrate a part of this distribution to kind of estimate the probability to observe a rare event of strong correlation. Okay, so this is this weight, W star. Okay, so here I pick up a cutoff at 0.1, but that can be 0.2, 0.15. This is not really important, this value. Okay, so this is just the integral of the largest part of the correlation. And this can be fitted as an exponential decay, and the important thing is to compare that to the size of the Hilbert space. So I take this W star and I multiply by the size of the Hilbert space, so that gives me how many events I have in a sample. And you see that these keep increasing here. So different colors are for increasing system size. So in this broad regime, up to a disorder of about 20, these rare events are present, and their number is not increasing linearly with the Hilbert space size, but it's increasing with an exponent. Okay, so we are not yet related to some other exponent of the problem, but an exponent which is between 0 and 1, this D exponent. And this is another way of seeing it. This length lambda Z is very big here in this green regime, and it decays, and it only crosses 1 over log 2, which corresponds to the Hilbert space dimension. Hilbert space dimension is 2 to the L, around this disorder 20. So looking at this kind of object, we kind of identify 3 regimes. One, which is our fat tail regime as before, okay, where this psi effective grows with system size, and this is what we kind of see here for different system size. Another regime, the yellow one, where there's no size dependence, but this length is still above a threshold, and the orange one, where now rare events are super rare. So in fact, you pick up a sample, you don't see it. And from time to time, you can see that. And this is also confirmed by looking at the maximal correlation per sample over eigenstate. You take a sample, you get the exponential eigenstate, and you pick up the maximal correlation. Okay, and you do the statistic on that. And this gives you exactly the same crossing point at disorder 20. Okay, so I should speed up, sorry. So our scenario is the following. So we have this, the blue regime, this is the ergodic phase. We have this rare event regime that we have first identified, and then we just discovered that the rare event can still be present here, but they become more and more rare, up to a point of about 20 in the disorder strength, where there's no rare event. Okay, maybe 1 minute of bonus. Because, okay, we could ask, what are these special eigenstate? Why at disorder 20, I can have like all the correlations which are 0, 0, and some 1. And so let's go there, for example, and this is what we have identified. They come by pair. They come by pair, and they are almost degenerate, okay, and they have almost the same value for the correlation. And so what we have just identified is they are like cat states. They come by pair, and there are a few body resonances. So here I try to sketch, this is not the exact form of the ground state, but this is very close to that, in fact. If you look at them like in the computer, this is what you find. And this is what it looks like a bit. It's not like a singlet, of course. This is like a pair state, like a Bell state, if you want, involving only 4 spins. And all the other guys, the black guys, are frozen. Okay, so these resonances are just touching a few sites. And if you go in the spectrum, this is how they look like. They are almost degenerate, and they are always neighbors in the spectrum. And their individual cat gap is below the natural gap of the spectrum. Okay, so I'm done. So this is the conclusion. So I hope I showed you that this MBL phasogram is richer than what we previously thought. We have identified, using this correlation function, a new regime of rare event where long-distance spins can get strongly entangled in an otherwise very localized background. And this rare event can, in some regime, dominate the average. Regarding this cat state, so this is a work in progress now with Fabien and Jeanne. So we want to understand how they proliferate and how they connect to the instability, various instability in the problem. Are they like the seed of the ergodic transition or not? Okay, so this we'll see. Thank you.
Thank you, Nicolas. questions?
Hi, just so in the green region, you said that the spectral statistics is Poisson. So by that, do you mean even all sorts of spectral statistics like spectral form? The spectral form factor does not have a ramp, and so it is completely.
The spectral form factor, we have not computed it. I know that this was a subject of controversy, but yeah, we don't have we have not computed it, so I cannot say for this regime.
Okay.
But in fact, the spectral form factor has some more technicalities and more like ways of computing, some filtering effect and stuff. So I think there are a few things under the carpet in the few papers that were published on this object.
Okay. And just one more question: this green region having Poisson statistics, but power law correlations. Is it? Do you think it's quite a generic statement, not really specific for the Heisenberg line, I mean, let's say quasi-periodic, flow KMBL, I mean, all sorts of, I mean, is it a very universal?
I cannot tell for the moment. What I see, if I compare to Giulio's and Marco work, they also have an intermediate regime for a completely different model with no symmetry. Their model has no symmetry, so easing with mixed field. And for us, of course, there is this conservation of the total spin, which might play some role, I guess. Okay. Then for the quasi-periodic, I don't know, because most of the people they say, oh, this is because Griffith's effect, rare event in the configuration of the disorder. But here this is random disorder, so there might be some Griffith's effect. But why, if you take like a random configuration and you take like an exponential number of eigenstates, only a few of them, although they have the same disorder configuration, all the guys, but only a few of them show this very particular response. So there might be some other thing as just the configuration in real space. So that means for the quasi-periodic, it might be that we also observe that.
Okay. Yeah, thanks.
Yeah. So I have a very naive question about, like you said that the exponentially decaying correlation I can see depends on what the quantity you look at. Like, for example, in one phase, in the XX core 2-point correlation was, I mean, the ZZ correlation was the one which actually shows that it is the exponentially decaying in the MBL phase, but not in the other phase, right? So my question is about, is there any understanding whether which one is to look at for a given Hamiltonian depending on the symmetries?
That's a good point. Okay, for us, in fact, the fact that you have this sum of SZ, which is a constant number, you can understand that the ZZ correlation is your guy. Otherwise, I don't know. There's no simple answer.
Okay. And I have another probably one naive question, like in your Hamiltonian, you have put a random field along the Z direction, right? So from a perspective of, I mean, equilibrium phase transition viewpoint, I have already broken the symmetry along the Z direction, right?
Sorry?
Of the Hamiltonian.
In the symmetry of?
Symmetries, I mean, SZ, because Z2 symmetry is broken in the Z2 symmetry is broken in the Z direction, right? So why I am looking at SZ then as a order parameter?
Here we don't have a Z2 symmetry. No, here this is a U1 symmetry. Okay. No, because the field in the Z is in the Z direction, so you cannot flip all. If you flip all your spins, this is not the same state if you want. Okay. There's no Z2 symmetry. There are models with Z2 symmetry.
Oh, so because you have a random field and this is between minus H to H, that's why the Z2 symmetry is not broken, you are trying to say? Or
yeah, there's no Z2 symmetry of the
Okay, thank you.
Okay, so you should. Let's take the last question and then we continue.
Okay, very quick. But do you expect the same phenomenology to appear in inverse participation ratio? Because this inverse participation ratio is related to Z-Z correlation, right, somehow?
Okay, first of all, the participation ratio depends on the basis where you compute it.
Yeah, let's do it on Z.
So let's do it on Z,
computationally.
right? And, well, it's not that, for one problem with the participation ratio, it's a more global quantity. So for example, if you're interested in this cat state, you could say, cat state, they should show up as a log 2 in the participation, right? Because one was square root 2, so it will give you like this. But the problem is, this log 2 will be hidden in the big background because the participation entropy or ratio integrate, in fact, all the sides, all the states. And so, because of course, this cat state is not as simple as it. Okay, there are some fluctuations around it. And so, because, yeah, we have worked a lot on the participation entropy with Fabien during the past years, and we have never seen. And we also did simulations at very strong disorder. And at very strong disorder, participation entropy is very
Just
small.
for the states.
It's very small, and nothing is visible there. So it doesn't seem to capture the rare events as this guy does.
Okay, so we will continue during the coffee break. So let's thank Nicola and all the speakers of this session.